Summary of Tableau 12, a potpourri of titillating applications. Part 2, rare events and probability sieves, pondering existence, the problème des rencontres, and the coupon collector. We began this excursus by going back to a basic, apparently trite property of probability measure, that of monotonicity, and discovered that a new perspective engenders subtlety and nuance which was completely unsuspected. Monotonicity gave us Boole's inequality, and out of Boole's inequality comes this elegant idea of a sieve. If you have a collection of events, A1 through AN, which I'm going to think of as bad events, if the sum of the event probabilities is strictly less than 1, then we can conclude that there exist occurrences of good events. We can deduce existence from a very, very, very simple test. We saw how, in the context of a two-coloring of a ball, it already gave us non-trivial information. But admittedly, this is a crude sieve. We discovered a much more delicate, nuanced sieve by turfing through an inclusion-exclusion paradigm. Now, the crux of this paradigm depends upon these inclusion-exclusion sums, and admittedly, they look formidable. But when you stare at them long enough, it becomes clear that they're actually saying something very reasonable, very intuitive, and algebraically perhaps not really that complex. Each of these inclusion-exclusion sums are looking at probabilities of intersections. And this immediately suggests to us a natural province where this kind of methodology is likely to be profitable. Intersections probabilities are easy to compute when we have independence, but perhaps also when we have near independence. And so again, we find independence running right through this. So if we have events for which conjunction probabilities are not difficult to compute, then we can put together an inclusion-exclusion framework. And of course, at this level, we've got an exact answer, but it's not very intuitive, is it? It's an ugly alternating sum, and it's not clear what it says to us. Things become completely transparent when there is actually near independence, when the inclusion-exclusion sums behave like the ratio of a power to a factorial. Now, where does the power come in? And that suggests where the independence is baked into the cake, or the near independence. If you have things which are vaguely, nearly independent, then these inclusion-exclusion sums are going to behave like powers of factorials. And the moment that happens, we find the Poisson distribution emerging beautifully out of the framework. So now we say that this apparently accidental discovery of Poisson in 1837 was not so much of an accident after all. It arises out of these independent or near independent trials. And so now we have a brand new perspective of where the Poisson emerges. We promptly put this to good use. We saw how we could use this Poisson sieve formulation to look at the Poisson approximation to the binomial. We saw how the Poisson sieves worked in le problème des rencontres, the matching problem of de Monmouth. And we saw how this formulation worked in the coupon collector's problem. Now you would say, well, these all look like fairly modest applications, with the binomial perhaps accepted. Do we have any real solid, weighty applications out of all of this? Indeed we do. Okay, so let me just sketch out domains of endeavor where you see the Poisson sieve working beautifully, gloriously. In one setting, it's that of models of brain function. And among other things we could ask, well, look, I remember individuals by how their facial features look. If I see a photograph of somebody after some years, I might well feel, oh, there's a tug in my memory. I think I recognize them. But maybe there are some errors in recall. If you're lucky, we don't make too many errors. At a high level, you think about a functioning organism like this, or at least a model of a functioning organism like a brain, as a computational device which is producing results where there are a few rare errors. And the moment we have this, we say, oh, maybe there's a Poisson paradigm which is embedded in here, and indeed there is. Right? In suitable models, we can argue that the number of errors is roughly governed by a Poisson distribution. And again, it comes out of the Poisson sieve. Another setting, let me take something which is very familiar to all of us, mobile telephony, satellite communications. Of course, the bane of modern life is the fact that our mobile devices sometimes drop our calls rudely, unanticipatedly, unexpectedly. Of course, if too many calls are dropped, then we get angry, we get furious, and we switch our service provider. We find another company. So there's an incentive for the telecommunications companies to provide a high level of performance so that people don't get distressed and angry with them. Another way of saying this is that with good luck and good management, it could well be the case that relatively few calls are dropped. Dropping a call is a rare event. What characterizes the number of these outages, these drops, whether it's for a mobile phone, or it is for an internet router dropping packets, or if it's for satellite communication, communicating images from Mars, where some bits are scrambled in an image? Well, with luck, these errors are all rare, and therefore, again, we anticipate a Poisson paradigm coming into play, and indeed it does. Yet another, perhaps even more modern application. In the modern day, technology has progressed to the point where we can create large numbers of very small sensors, sensing all kinds of things we are interested in. Things like climate, pressure, temperature, pollutants. And we can create large numbers of these sensors at very low cost. And so this gives us now a new way of trying to actually monitor things in our environment. Well, let's say that we're worrying about the consequences of pollutants in farmlands. Imagine with a crop duster airplane flying over a large field where there is irrigation, and you drop in sensors all over the field at random. Each sensor checks for certain pollutants, certain chemical contaminants. Now, these sensors can collect information, and then they send information out. And if any of the sensors or a group of them say there are pollutants, then we know we have an issue, and then we can go ahead and deal with it. Active management will not be needed. But of course, this creates new issues, you see, because if you're going to create very tiny sensors, if the sensor detects anything, there's got to be a mechanism by which it can get the information out to the individuals monitoring the situation. Well, how does a sensor get the information out? Well, it can't simply say, pack up my bag and walk down out to the edge of the field and say, by the way, there was a problem there. A sensor can't do that. How does it do it? Well, a sensor does it by broadcasting the information using telemetry, electromagnetically. In other words, you're going to have to equip the sensors with antennas and batteries. But if the sensor is very tiny, it's impractical to put a large, clunky battery on it. So the batteries are limited in power, which means that the range over which a sensor can communicate is also limited. All right, if that's the case, how do you get information out? Well, perhaps by collaboration. A sensor, me, I, detect something wrong, and I, sotto voce, because I've got a very small voice, just broadcast in my local vicinity. Guys, I've found a problem, I found a problem. And these mutterings are seen by neighboring sensors. They pick it up and pass it on. And if you keep doing this, eventually, with luck and good management and good network protocols, you might find the information emerging from the field to some monitoring devices on the periphery. I'm giving you a very stylized way of thinking about this problem. And now we can see that we can maybe get the information out. But this now begs a mathematical question. If my sotto voce utterances are to be eventually taken out of the field, then somebody has to be able to hear me. There's got to be a sensor, a person, an individual, an antenna and a battery in my near vicinity. If I throw in too few sensors, then I'm going to lose that. So this says I'll need to analyze how many sensors I need to throw out there so that every sensor is connected to a neighboring sensor and that the entire assemblage forms a connected network of communicating entities. This is a coverage problem. In the classical theory of advanced probability, it's called a mosaic process. Right? Imagine that each sensor can see in a small region around it. Right? It's something like somebody is painting a room, but the painter is very messy. So he keeps dropping big blobs of paint on the floor. Hopefully, none of the blobs is very big. Okay, this is a small powered antenna. Right? But if you throw enough blobs, then the whole floor will get covered by connected blobs. Okay, here's a setting for a mosaic process. We're talking about when will it all be connected so that I can get information out. The analytical question here is going to be then, what is the chance that if you throw enough sensors, that one sensor is isolated if they have a small radius of communication? This, with luck, is a rare event. And if you throw enough sensors, then the chance of somebody getting isolated is rare. How many sensors are isolated? How many blobs are stuck on their own without connecting blobs? Well, it should be governed by a Poisson paradigm. We have a small number of errors, and they're rare, and they are approximately independent of each other. Not quite. There's a level of dependence, but with luck it's weak. And of course we can analyze this. But of course you understand that analyzing settings like this is going to require correspondingly more and more formidable algebraic machinery, and I will not do that here. This was to give you a feel for the vast scope of the applications of these limit theorems involving the Poisson in a completely unexpected direction. The central limit theorem gave us guarantees for typical events, centrality. The Poisson distribution tells us things about rare events. We should finish up our story with just one big slogan to complete all of this. And here it is. Rare events follow a Poisson law. All good things must come to an end, and so too this course. We've covered a lot of ground in 8 weeks. And I hope I've been able to communicate to you a theory which is rich, which is luxurious, which is sumptuous. It's built upon very simple, basic principles. But these principles inform applications which are exotic, which are beautiful, which are portentous, which are real. And if I've given you that much, then I'll have given you something valuable. But I shouldn't let you run away simply with a saying, well, here's a formidable mathematical apparatus, and some of it was really tedious and difficult. Yeah, the applications were neat, but boy, understanding how to apply these was not easy at all. It's beginning to feel like drudgery when I put it in those terms. But no, the discovery of beautiful ideas like this is at its heart a very human endeavor, and this endeavor carries a great deal of satisfaction inside it. At its heart, this endeavor actually is fun. And so, if you will indulge me, in our last concluding adieu goodbye to you from me and all our chefs who contributed to this enterprise, I'll begin with a word from James Clerk Maxwell, exalting the value of frivolity, of fun in discovery.